got a problem here that talks about the work that's done to remove a person from Earth's gravitational hold. And ultimately what we're getting down to here is we're looking at work when it's done by a force that's not constant, but a force that has a varying value over some distance. And so that's something we need to look at because it applies to multiple situations. It may apply to springs, it could apply to drag force, as we know, and then here it can also apply to the force of gravity. If we look at someone standing on the earth, so a little person, and we're going to remove them to the point where they're no longer affected by Earth's gravity, okay? There's work that has to be done because we know there's a force of gravity, and so we have to overcome it. So let's first take a look at two equations. We've got our work equation, work equals, we're going to do it in terms of an integral, F, with respect to the distance over which that force is applied. But we also need to know the force due to gravity. And the force due to gravity has an equation, and this top part's all constants. It's going to be the gravitational constant times the mass of the Earth times the mass of the person divided by r squared, where r is the distance between the person and the center of the Earth. So you can see that as this person moves further and further away from Earth, r is growing, so the force is decreasing. So we ultimately are going to look at the work that it takes to remove the person from the Earth. It's gravitational hold. Okay, so a couple things before we get started. One, we're going to start with a distance where the person is the radius of the Earth away from the center of the Earth, because we consider all the mass to be right at the center of the Earth. We also have to look at, okay, as we move further and further away, even though this R value is getting larger and larger and larger, it doesn't actually completely make the force disappear. So it would take us moving the person an infinite distance away to get the force to zero, to fully escape Earth's gravitational hold. So we're going to end up integrating from the boundaries of starting at r all the way to infinity. And the cool thing with calculus is we can do that. The other thing we have to consider is our equation's always been in terms of x, and this equation is in terms of r. So really we're going to integrate with respect to r, but it's not that bad. One more thing. As we move in this direction, radially away, that's the positive direction. And Earth is pulling back with a gravitational force. So that means that the force is in the negative direction. Okay? So now that we've kind of wrapped our heads all around this, let's write the equation we're going to work from. So work is going to equal the integral starting at r going to infinity of negative g mass of the Earth times mass of the person divided by r squared dr. So not so bad. Okay? And then, as we've learned earlier, we can pull out constants. Well, this top part here is all a constant. So we're going to pull that out in front to make this a little bit easier. Start making it look a little bit cleaner too. Of 1 over r squared dr. And you might start freaking out thinking, oh, I've got something that's underneath. It's the denominator of a fraction. Do I have to start looking at some weird integral? And the answer is no. You can actually rewrite this so that it's a really simple integral, something you've done before. So negative g m over r, integrating from r to infinity. 1 over r squared is the same as r to the negative second. And so now it becomes really easy. You're just undoing the power rule, right? So negative g m. So remember to undo the power rule, raise it up, put it under. So -1 or -2 raised up is -1. Put it under. So now we're going to have negative r to the -1, and we're going to evaluate from r to infinity. Okay. Well, really, we can end up rewriting that. So we have negative GM m times -1 over r. We're going to evaluate that from r to infinity. All right, so you're starting to see how simple this really can be. So now let's go ahead and plug in our values. I'm going to evaluate that from -1 over infinity minus -1 over r. Okay, well, 1 divided by infinity, that goes to 0. So we see that drop out, okay? And then we see here -1 minus, so that's really like plus. So we end up with negative G m over r, okay? And that's going to get us our work in terms of how much work it takes for us to leave Earth's gravitational hold. And really, when you end up plugging in all the values, you get something about 3.7 times 10 to the 9th joules, okay? And the negative sign just means into which system the work is moving. So you can essentially ignore it for the moment as we consider this. And that seems like a ton of energy. But in reality, if I have a 100-watt light bulb, okay, there's my little curly Q in the light bulb. If I have a 100-watt light bulb and I let this run for an entire year, if I were to total up all the energy that took, it ends up being 3.1 times 10 to the 9th joules. So really, it's not that far off when you think about it. So for how far we'd have to go to escape Earth's gravitational hold, that's really not that much work or not that much energy that we need. So it's kind of cool. You can take this idea and translate it to other problems that you have with varying work.